Alright, so we already talked about gases yesterday. Today we're going to go up in energy a little bit and talk about liquids. So the goal for today would be use that kinetic molecular theory to talk about liquids, define vaporization, the idea of liquid changing into a gas, and then also solidification where liquids will change back into a solid. So freezing. So in a liquid, we have now a form of matter that will take the shape of its container just like a gas would, but it also holds a definite volume. So that's why you can measure something out in a graduated cylinder and then pour it into a beaker and still have the same amount. You couldn't necessarily do that with a gas because a gas always fills the container around it. This is because the attractive forces are more prevalent in a liquid as compared to a gas. And there's three forces. See if you guys remember the intermolecular forces. There's dipole-dipole, London dispersion, and hydrogen bonds. Do you guys remember the one that's the strongest of those three? Well, I think you were. Hydrogen bonding is the strongest. The weakest one is London dispersions. But hydrogen, because we see that in water, why water tends to cling together. Some of the properties of a liquid is that they are not bound together, but they move about constantly. So like a fluid, we mentioned, is a gas or a liquid and can take the shape of its container. So that first property there, relatively high density. Most substances are like hundreds of times denser when they're a liquid state than they are a solid. They've been compressed down from their... I'm sorry, not from a solid, from a gas. They've been compressed down from their gaseous state and are now much denser when they're in liquid form. They're relatively incompressible. You know, even deep in the ocean, you might see liquid being squeezed together a little bit more, but that's about it. Even down in the ocean, it's relatively incompressible because, like with a gas, we can pump a lot of gas into a small container and keep pumping more in and squeezing the gas to a higher density rather. But liquids, they don't have that ability to be compressed. Once we try to fill a solid container with liquids, it's hard to put any more into that. Liquids also have a great ability to diffuse, meaning you'll see one liquid quickly travel throughout another liquid. We mentioned this with gas, but we also see that with things like food coloring, for instance. You may have done an experiment like this where you drop a few drops of food coloring into a liquid of water, for instance, and it'll spread. The concentration will be equal throughout as it spreads. You might have noticed too that when you heat that up, it also dissolves better, which we'll talk about. And this is because even though it's not as much as gas is, we still have that constant random motion of the particles causing that diffusion. Note that diffusion is much slower in liquids than it is in gases because the liquid particles are closer together, therefore bumping into each other more, preventing that from happening, slowing it down when they're attracted to each other. And like I mentioned, if I do increase the temperature, diffusion occurs more rapidly. I had some hot chocolate this morning that wasn't completely dissolved. I threw it in the microwave a little bit longer, and then a lot of that powder dissolved without me really having to stir it anymore. So you see that heating liquids up allows, and that's my example is a solid into a liquid, but heating a liquid will help the other liquid dissolve as well. Another property of liquid is surface tension, and I don't know if you guys have heard, there's a lizard that actually takes advantage of the surface tension of water. It's this one here.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, maybe run on water. It bicycles its hind legs, and the tail becomes a counterweight. We can't know what the snake is thinking. Did it really want to eat the lizard, or did it just want to show?
So I always like to bring that up when we talk about surface tension, just to so you can see, obviously, that we know water does have a surface tension. If you've ever tried to jump into a pool, you know you're going to experience a lot more pain with like a belly flop versus if you dive in and break that surface tension. Same with like pushing a push pin into a wall. You know, a nice sharp pin with very low surface area is going to push very easily. So if you make yourself kind of like a pin and have a low surface area, you're going to be able to easily push through that surface tension of the water. So you've probably heard just an everyday conversation breaking the surface tension as well. And that all has to do with those hydrogen bonds, especially when we're talking about water in a pool or any body of water. The last thing I want to talk about is capillary action. That's the attraction of surface to a liquid of a surface of a solid. If you remember in lab, we have this thing called a meniscus that forms when we try to measure water in a graduated cylinder. I'll bring that up here. So graduated cylinder meniscus. So you see this little curve that happens because the liquid is sticking to the sides of the container. We see it's a little bit dramatized in the drawings, but it does happen. You do have to read by the bottom of the meniscus because the sides of the container will stick to the liquid. Last but not least, it's kind of what we probably would focus on the most, is evaporation and boiling. The process by which a liquid or solid changes to a gas in general is called vaporization. Now, whether or not it's bubbling is what determines whether it's boiling or evaporating. If you spill a liquid and the surface of the liquid just kind of becomes a vapor because it's at a higher energy than the rest of the liquid, that's called evaporation. But a boiling liquid would be one where we see bubbles forming inside the liquid, vapor forming inside the liquid, and then escaping to the surface. Boiling doesn't have to happen at high temperatures. We can see if we evacuate a tube. I'll bring in this demo later, but if we evacuate a tube or a jar, with a tube, we can remove the air, and water will actually boil at a much lower temperature. You'll see bubbles forming even though it's like room temperature. So that's kind of the difference between evaporation and boiling, is you're looking at the surface versus the whole liquid as a whole. Finally, the opposite. I keep saying last but not least, but there's always one more topic.
Do you have isopropyl alcohol, like regular rubbing alcohol? We found lots in the shark, and we're going to try to preserve them.
But I think this is the last here with the freezing. We're talking about formation of solid from a liquid. So when a liquid is cold, the average energy of its particles decreases. Another word for that would be solidification. And then we get to solids. So kind of ran through those properties rather quickly. Just to go back to capillary action, something you can do at home if you ever wanted to try this with paper towels. Paper towel rainbow. There is...
Just wanted to start a business.
Yes, you need to sell those.
This has an epic version of Somewhere Over the Rainbow playing in the background, but we're just going to kind of look at the key points here. They're just going to add some food coloring into the cups. They did 4 with. You can see they filled it up. They folded some paper towels and then put the paper towels in between the cups, so you have a full cup, empty cup, etc. And they laid them all out like that. So this is what it looked like at the start. You notice those cups are empty in the middle, but over time what happens is those paper towels will absorb the water due to capillary action. It's the quicker picker-upper. It brings the water up against gravity. And it's made of plant material, which would make sense because plants use that capillary action to get their water. But over time, you see those water levels will balance off. You have a nice little rainbow of paper towels there. So something, if you ever get bored at home and you want to try that, it's a relatively easy experiment you can do without too much danger. Like I said, that's all I really have for liquids. I put that homework 10A up today, but technically there are 2 questions that you won't be able to answer until tomorrow when we talk about solids.